Yeah, so we covered attention last day and in very much detail. But there is a small problem with self-attention. Okay. What is the problem? Let's write a sentence. Okay. Give me a name. Let's say Rohan. Rohan shot Mohan with a gun. Okay. Now, this can mean two things. Okay. Let's dissect this statement. Okay. This can mean something that Rohan has shot Mohan using a gun. So that's our meaning one, right? Meaning one is that. Our second thing can be what? Rohan has shot Mohan with something else, but not a gun. And Mohan has a gun. So it's like Mohan with a gun. So Mohan has a gun and Rohan has shot Mohan. So this is my meaning too. So now notice something in self-attention. What you do? We find out the how one word is related to the other word. So or like what is the context? We are finding out the context after attention, right? So here we have two different contexts, right? One context is Rohan shot Mohan with a gun, as in the gun is with Rohan. The second context is what? Rohan shot Mohan with a gun, which the gun with is with Mohan this time. So the gun can either be with Rohan or with Mohan. So here we have two different meanings. So how do we resolve this? How do we resolve this? Okay. So this kind of problems we cannot do with a single attention, right? Like single self attention cannot solve it because one attention will give you one context. It cannot give you two different contexts. So one time it can give meaning one time it can give meaning two. So it can't give both of them, right? So this kind of problem can be solved by multi-head attention. What do I mean by multi-head attention? We basically, let's take a detailed example this time. Let's say we have a word, let's say apple, okay, and we have another word. um, why can't I find a word? Let's not do apple. Let's say give me like any word. Let's say, yeah, let's say apples, and this one is banana. Okay. Okay, so let's say this is some embedding vector of size 2 cross 6. Okay, 6 for all the letters. Okay, so this is for 2 cross 6 vectors. Okay, so normally what do you do? Normally what do you do? Let's say apples and banana are my input, right? Okay, this can be anything, but I'm saying apples and bananas. These are my two input, right? This is my input vector. Input vector. Apples, banana. Does not make sense here, but we'll explain it. So let's say what happens normally is this is one attention, and we run both of them to this attention, and then we get a result, right? That is the whole thing. That is what happens, right? In the attention, what happens we have taught you. But this is what happens in normal attention, right? So, but here we will do multi-head attention. What do I mean by multi-head attention? We will use attention two times. So, this is one attention block. This is another attention block. So, this apple and banana will go here once, and apple and banana will go here once. And they will give two different outputs. Okay. So, this is what multi-head attention usually means. Okay. So, let's do it in a general kind of form. Okay. So, multi-head attention does not mean it will have only two. It can have three more anything. And each of them are called heads. So, let's say in our case, let's say we are considering three of them. Okay. Uh, wait. How can I copy paste this? Let me make this shorter. Huh? That's better. The drawing classes has to be there. Okay. Now each of them will have their own q. Let's say this is q1, v1, and k1. They will have their own versions of kqv. So this will have k q2, k2, v2, and this one will have, let's say, q3, K4 3 V3. So every one of them will have their own set of queries, values, and keys. So everything what will happen now is that we'll be applying attention to all of them differently, okay? And we will get a result for each of them. Now, if you know something, if you remember, the whatever my input was, you were getting a output of the same length. So of course the output will also be, let's say this is my out 1, this is my out 2, this is my out 3. So what will be my output size? All my output sizes will be nothing but 2 cross 6. All of them, all of them. So because we saw the sequence we are inputting, the out sequence will also, the output will be also the same. So the 2 cross 6 is not because like, yeah, apple is of two sizes. 2 cross 6 means see two words and 6 letters. So that's how I am doing the embedding here. Okay. Next, what we have to do in multi-head attention is we have to combine these. Combine this. So we have to combine this and we'll get this. I'll shorten this to fit in the diagram. So this is out 1, out 2, and out 3. So what we did here was concatenation. We concatenated all the results. So see, as I said, remember, Rohan shot Mohan with a gun. So this one will be one context, this one will be one context, this one will be one context, and out of that we got all the contexts mixed into this one matrix. But as we know, our output has to be, the output has to be of the form 2 cross 6, and this is what, this is not 2 cross 6, this is, let's say this is 2, because the width is same, no, so it's 2 cross 18. So we have to make it 2 cross 6, right? So what we do, we multiply this with a, we'll multiply this so that we get a 2 cross 6. So we'll multiply this, and this big matrix of weights is 18 cross 6. This is just a weight matrix, okay? Weight matrix. Okay. And after this, what will be my result? I'll get my final output out. That will be 2 cross 6. So this is how multi-head attention works. Okay. Basically, these are called heads, and these heads are combined together. Okay. So you have a big query vector. Okay. You have a big query vector, and you have a big, basically you have a big query vector and key vector and a value vector, and you project them and you get this q1, q2, q3, and then finally when this happens you get the output like this. So this is how the total thing works. And this weight matrix, if you see, okay, how the multi-head attention is written in the paper of attention is all you need. It's basically written as this. I'll write it. It's basically concatenation of all the heads into w0. This is and now what we did, we just found out all the attention from all the heads, we concatenated it, multiplied with a W0 weight matrix, and we got the final output. So this is how multi-headed attention works. It's very simple. This is how what the basic intuition for multi-headed attention is. So now we'll talk about layer normalization. Layer norm basic. So see, we are teaching you everything separately, and in the last lecture we'll bring everything together to make the transform. Okay. So now why did we, like, the layer norm, where will you find in the alphabet? It is written add and norm. So that is the layer norm. So what happens usually is that we have data which is very scattered. Let's say, let me draw this. So let's say this is my thing, and let's say the data will be very scattered, like here, here, here. Wait. Let me draw it really with a different color. I think it will bring more essence. So the data will be very dispersed throughout the space, right? So we don't want to work with such data because let's say if there is an outlier, now what is an outlier? Let's say you have all the data in this range. Let's say I am declaring a number line and all the data is, let's say, here, all the data, and there is one data here. So this one data will affect this data, and maybe let's say the mean will come around here, but the mean should come around close to here now. So that is why what we do is that to remove such outliers and everything, we do um, some normalization. Some normalization. So this kind of system, what we do, we try to bring this random system into something which will have a mean of 0 and a variance of 1. Okay. So how do we aim to do this? We basically get the formulas of mean. Okay. So what is the formula of mean? For mean is what? Sum of xi by k, by means k is, let's say, the total number of terms, and variance is what? Variance is sum of xi minus mean whole square by k, right? So we use these two equations and solve these to find in term of xi. And now when you solve xi from these two equations, right, so you get something like this: xi is equal to, means the final xi, okay, not the initial xi. So after the normalization, you'll get xi is equal to, let's say, we name it xi dash. Okay, xi dash is equal to xi minus mean this whole by root of my variance. If you solve that equation, now you would say, what if my variance is 0, right? So of course we don't want the variance to be 0, then xi will become like a very big value, right? So that is why we add a epsilon here. That's, we are basically adding it for numerical stability, so that if the denominator becomes 0 by chance, it will not be 0 actually. Okay. So this is what we are basically doing. We are normalizing the values to have, to bring it closer to each other, or like, so that we don't have that many outliers, or we don't have that many outliers causing problems with the mean or the variance in any chance. We are trying to bring them close to each other. As simple as that. Think it of like that only. We are normalizing the values to some new values. So that is what we are trying to do with layer norm here. So now we'll talk about residual or skip connections. So if you see something, sometimes instead of going into the multi-head attention or the feed forward in a thing, no. So it skips it. Wait, let me use a different color. This is here added in the add and norm. See, it is not going through the attention layer, or it's not going through the feed forward layer here, here also. So what is this? So sometimes what happens, I'm just talking about the simple skip connections or residual. Okay. So what happens is that we try to bypass some networks. As simple as that. Skip connection is basically where we bypass some networks. We are feeding the output of one layer into the input of the earlier layer. So see, whatever the positional encoding was there, we are directly moving the output to the as input of add and not, instead of going through the whole attention thing. Okay. So the reason we actually did this is due to something called a degradation problem. So what it has been noticed basically, whenever let's say there is overfitting, or let's say we are making complex models, right? So we are building a transform, it's more complicated than a simple, let's say, linear regression, right? So since it has more layers, more training, and more complex models, so sometimes what we see over time, the more we train, we are losing performance. So for that, we are doing this. So let's say, let's consider the like a small. This is one neural network. Let's say this is one NN1, and this is, let's say, NN2. Okay. So this one is a very simple neural network. Okay, this is simple. Let's say this is simple, and this is a very complex one. Okay, it has a lot of layers. NN2 has a lot of layers, lot of complex in it. We are not going to detail how it looks. So we are talking about it has a lot of complexity in it and everything. Okay. Now what we want to do is that we want to use the weights we did in let's say simple is working fine. It's a simple network, but let's say if you are using a classification problem, you have a knife based classifier. It's a very simple classifier, and we are using that, let's say here. Okay, we are using that here now, the weights of classification. And now the complex let's say the complex is to solve mathematical equations. Now, if we tell it to do a, let's say, if we are using the weights of the simple classifier, you might think that the deeper neural network, or the complex one might work better, right, than the simple one, but they don't. So reason is basically this, because if we are training on the weights of the simple one on some complex neural network, or the complex, any kind of complex model, right, it won't work, because it will start losing what do you call it? It will start losing performance. So what we you do after this, we basically sometimes skip the sim parts. Let's say we can come from here to here, then we can skip two parts and then go through feed forward. So what it's doing, it's skipping training sometimes, skipping important parts of the transformer, or important parts of the neural network, so that even it does not go through that extensive training through all the parts, and does not degrade over time. So this is what we do in skip connection. And usually what we do, we just, as I said, we are adding the output of one function as the input of the next function. So let's say my output, the function we are trying to find is hx. So that will be nothing but fx plus x. Why? So because see what we are doing. Let's say this is my fx. Wait. This is my fx. This is my fx. Let's say the input embedding position I get. This is my fx that is going in. Normally it would have gone through the attention to find the non, but no, we will actually just directly add it. So that's a plus x. This is simple addition. We are adding the output of this to the input of this. The input of this would be that x vector, right? Multi-head attention, say you get that x vector. So we are adding the x to the fx, whichever function that is behind, to finally find the add and the norm part, that is the h of x. So we skipped the connection here. So yeah, so you have to implement all of this there. So with this we end our today's lecture, and I don't we will have two more lectures and we'll finish Transformers. See you guys. Have a good day. And enjoy solving the quiz in the collab notebook.